So good morning, everyone. In the end of the last class, one of you were asking about how this is going to normalize. That's in fact true. That was a mistake from my end. I'll share the screen and we'll show you that. That's a very good point. I missed that in the, that was a mistake. There was a mistake here. It's not just so from the whole matrix. While we are computing this correlation, we are computing that on that matrix for which the mean is made 0 in both cases, right? So only for those things you need to compute here. So it is like if you are computing, as the same example I have given, a bar dot b bar by modulus of a into magnitude of b. If you are doing that, these two should be same. So for that reason, this was a mistake here. Okay. Thanks for pointing it out. That's a very important point. So for you I have rewritten the equation here now. Anyways, once I upload the video again, you could take a look into this. You could pause the video here and have a look at this equation. So basically all that is now changing is, instead of earlier if you have written this equation, just make correction here. You subtract from here f bar of ij and then take square of it. That's all. Similarly here, you come subtract from h of uv first the average h bar and then take square, or means take and sum them up all and then take square root. That's the correction. Okay. Is everybody fine with it? Then let me also write the equation for f bar of ij, which would be equivalent to, well, I have this again. If you are referring to different textbooks or papers, this notation would vary. Here I considered, let's say, k to be an odd number. So it could go from, let's say, k could be -1 to 1, for example. Okay. So in that case, I have k to be equal to 3. So that then it will be minus k by 2 to plus k by 2 would give me -1 to 1. So one, if you consider k as width of the window, it comes in one way. So that's what we considered here, k to be an odd number and width of the window. Okay, for example, then 3 by 2, 1.5, you consider it as 1. So then it varies from -1 to 1. Or similarly, let's say k equal to 5, your width of the window is 5. So 5 by 2, 2.5, you vary u from -2 to +2, u being an integer value there. Or else you could have considered also from the center, this half length of your window is k. Okay, some books consider it in that manner. So in that case, it would be simply minus k to plus k, where your window size is 2k plus 1. Okay, perhaps that is a better notation to follow, because you don't have to worry about the seal value or floor value of k by 2 you are taking, and you also don't have to worry about whether it is an even number or an odd number. So that's also is a, I would say, is also a good notation to follow. Okay, just that here I considered the whole window size varying from minus k by 2 to plus k by 2 here. Say for example -1 to +1 if I consider, then what would happen? For example, -1 would come, 0 would come, and 1 would come. In that manner I have kept k plus 1. Okay, so just it is enough if you realize here that the total number of summations you are doing, you divide it by those many number. Okay, if it is a matrix of k plus 1 by k plus 1, this turns out. So this would make your so just I don't want to make a sudden shift in my notation. So let me put k as let's say an odd number. Okay, that's one thing I would keep here. And what else should I keep there? Yeah, I should somehow, I think you got the message here. Okay, you simply move to a notation where you would say the size of your window is 2k plus 1. Okay, so then k can take any value, doesn't matter. 2k on one side k and on another side k. So maybe that's what I would write the notation here, just to avoid let me stop the video here so that I could write here. Okay, so what I would do is I will slightly rewrite. Please make a note. I'm not going to have it in slides as such, so you just make a note here. So let the window size be, just to avoid any confusion in the notation, will be 2k plus 1. That means on whatever window I have here, okay. Again, I could have considered different window sizes in both U and V direction. Then I just need to change UV values there accordingly. But for now, I assume that this is varying. It is a symmetric one with number of rows and columns being same. So what does that mean now? 2k plus 1. That case, my you also please make a note of that. Gamma, I am normalized cross correlation, I am referring it with gamma. This is depending on the pixel location for which I am computing. Let's call it I comma j. And I am going to vary now u value, this being minus k to plus k. Okay, so notice here it is varying 2k plus 1 here. Similarly, v value minus k to plus k. So if you want, this whole length is 2k plus 1, right? If you take the some center pixel here, so this length is this, yeah, you take somewhere here. So this length is k. Similarly, after this pixel, okay, I'm considering this. So then this length is k here. Similarly, this length is k here. Of course, there is a 0th pixel, index 0 pixel is there at that location. Similarly, you could write in this direction also, this is k and this is k here. Okay, this is your 0 location. Okay, so v minus k to, hope that is clear. The normalized cross correlation value for location I comma j is equal to, you can tell me, there are two summations, u varying from minus k to plus k, v varying from minus k to plus k, f of, tell me now, f of,
I plus u,
very
comma
good,
j plus v.
j plus v, good, minus, let's call it as f bar. Okay, and let's say you are computing for I comma j, this value, it is dependent on ij location, right? So this you multiply with which value, let you are calling the kernel as h, so h of,
U comma v.
very good, minus h bar, let's call the average that you are going to subtract from it, whole divided by, now what you should do, take the first one, u again minus k to plus k, v minus k to plus k, f of I plus u. Pay attention here, you have an assignment, you have one programming assignment question where you have to implement this whole stuff. Okay, so pay attention, that's another excuse to pay more attention here. F bar of I comma j, this whole square. Okay, be clear that you are summing up this is like a bar dot b bar by magnitude of a. How do you find out? Suppose if you have x naught, x1, x2, how do you find it out? Square root of x naught square plus x1 square plus x2 square to normalize it. In very similar lines, you are doing it, except that you are subtracting mean, that's your resulting vector there. Okay, yeah, this of course you take square root of this. What else you have in the denominator? Similar lines, u is varying from minus k to k, v varying from minus k to k, h of u comma v minus h bar, right? This whole square. Okay, so notice the square is there, you do for each element square and then sum up, and for the whole you are taking square root. That's all. Then if you want, I would also write here, how do you compute f, you tell me now, how do you compute f ij bar here? Tell me the equation now. How do you compute f ij bar? Use a similar notation of what I have taken so far and tell me now. I give you the f I have given you. I have told you the location. You tell me now, how do you compute the mean value?
1 by 2k plus 1 whole square.
Very good. Then
Summation u
uh,
from minus k to k and v also from minus k to k.
right? Then what?
F of
Hmm.
I plus u. No,
Hmm.
f of, yeah, I plus u comma j plus v.
Very good. Very good. That's all. This is nothing but you are summing up all elements, okay, centered at ij with the window size of 2k plus 1 in the rows and 2k plus 1 columns, okay, k above and k below. You are summing them all. You notice here total number of elements will be 2k plus 1 whole square. So you are dividing with that, as simple as that. Okay, now you tell me the equation. One of you tell me the equation for h bar now. How do you compute h bar? You have told for F bar. Now I would like one of you to tell me for H bar also. You have H bar here, right?
Similar lines, sir. 1 by
Yep.
2k plus 1 whole square
Hmm.
summation, same summation, and h of u comma v.
That's it. H of u comma v. Okay. Is everybody clear with that? Can I move forward? This is very important thing. You are going to have an assignment, programming assignment, one question on that. So make sure you are clear with these equations also. Okay, that's what you would require. Now I'm moving to again the uh, slides. Okay, see, you please write your own notes in this notations and all, because I have not put the effort to prepare these slides myself. I am just using some slides where the variables and all are different. See, for example, you could notice you would still find out equations similar to that, except that I am following my own consistent notations. Say, for example, in my place where ij are there, uv are there here, and where I have uv, they have xy. Where I am actually keeping row column wise, they are combining everything and putting here as for all xy values. So there is some notational changes are there. This is just for a reference for you. I don't want, I did not want to write all these things on my own. You please, that's why I wanted you to prepare your own notes. Okay. So, but still you could figure out here what the equation is. So this is the correlation you are doing after subtraction of means. Okay. And here the square of it. Okay, this hope you also see now. This is something to do with variance also. Given a sequence, how do you write normalized cross correlation? The same thing you could have expressed in terms of variances also. But here I wanted to show you an interpretation like the dot product. So that's why I have written it in this manner. Okay, right. So this is done now. I will continue it with a few more points for the uh, template matching. I'll also tell you. See, this is where we started. You wanted to figure out where this particular object is. And then we have seen that. Let's start with mean square difference, sum of squares of intensity differences. That's what we, for each pixel here, you subtract, you keep the center with some pixel where you want to find out the matching, subtract the corresponding pixels between these two windows, right? Square them and sum them, look at where it is minimum. Then we realized that if we assume that the average intensity in a given window is constant over the image, then there is only one term, a minus b whole square, a square plus b square minus 2ab. Okay, then a square also you could consider constant. B square is anyway related to this, so nothing to minimize about that. And 2ab is turns out to be finding out a cross correlation between the two. Then we further took some more steps by identifying what the problems are there. First problem being the very assumption that you want to keep it that f will be constant. Okay, this window average value is constant is not always true. So we introduced normalization of that. Another problem we realized is the intensities between this and this could vary. So that's why we subtracted the mean also. And that's how, and also to normalize and bring it to values of -1 to 1, just like a bar dot b bar. When you divide it by the magnitudes of both a and b, you will end up with just the range of -1 to 1. We use a similar idea here. So that's where we started with sum of mean square differences. Okay, sum of, because you had the sum mean of sum of square differences of intensities. That's what we started with. From there we reach it to cross correlation. From there we reach it to normalized cross correlation. That's where we are right now. So that would hopefully would give you that. And this image tells you these are the kind of things you are going to do in your programming assignment. You are just going to implement the same equation that we have written. And for example, if you are doing for this image, and if you are drawing the values, obviously when this is around this placed here, you would see a good match there. So that's why you are seeing white here, whitest being 1 and darkest being -1, I think. Okay, black being -1 and white being 1. So you would obviously would see here the best match here. Of course, notice here, even if you are placing it slightly here and there, except at those border lines, in the rest of the places it would match. That's why around the white spot you have other not that high value, but very close to that, you have values around that. So this would be your assignment. Okay, this used to be given in the newspapers, where they call it, where is Waldo? They used to ask it. People used to, so this guy is there. Okay, template. Now you have to see the whole image and where this guy is there. Okay, so that's the assignment for you. And then you would see that Waldo is here. You need to implement simply this normalized cross correlation here and do it for your assignment. Okay, so this is the kind of thing you would be getting. You would do normalized cross correlation with respect to this mask throughout the image, and that would give you this. And you already know from the previous class and the class before that on how to deal with boundaries. The same thing would apply here. Anyways, while you are looking for matching, you would ignore the boundary pixels. You just look at in the valid regions to find out where this Waldo is. Okay, any questions so far before I give you a few more examples?
Sir,
Yes.
here the scaling is important, right? Like
You mean, are you referring to scaling in intensities or scaling of the object in terms of pixels?
object in terms of pixels.
That's right. That's right. Still, we have not overcome that disadvantage of this current approach, where if the object got scaled by a factor 2, there is no way you could find out the matching of it. That disadvantage is still carried forward here. We have not addressed it yet. We only addressed, with the help of subtracting the mean, that if there is an intent for the same size, by size we mean the number of pixels, if there is a difference in intensities, that too either getting added up with some value, mean remaining the same, in other words, that is the only case we addressed so far.
Yes, sir.
Anyone would like to give it a try, and why in the first place we subtracted the mean? That has the answer. Anyone, any student would like to give a try to answer that question?
Intensity variation.
Right. See, the very purpose we introduced it is, for example, in this, my Waldo might have got, I might have added here, let's say, some 50 intensity, extra 50. Assume that this is in between 0 to 100. I could simply add 50 to every pixel intensity. So it would come from 50 to 150. Still, if you are subtracting the mean, it works out. If you are not subtracting the mean, it would work only when this intensity range is exactly same as this intensity range. So unless I subtract it, it will not take into account, or it cannot compensate for intensity variations. Here there is another example here. Suppose if you want to detect a car, okay, how many, where, yeah, this is a very primitive way of doing it, but still it's an interesting way of doing it to begin with. What is what if the template is not identical to some sub image in the scene? Okay, so uh, yeah, see, again, this, as one of you had, this is still a car, okay, but this size of this car is different here. Okay, both the cars, but unless you have an identical car, you won't be able to detect. or even if you detect, the location could vary here in this particular case. So now we are looking at what are all disadvantages are there. As one of you rightly pointed out, scaling in the pixel space cannot be addressed. And second one, both are cars, but in their shapes there could be, all cars won't be even from the same brand, won't be identical. You find out finer changes there, that cannot be taken into account. It could be the same model, exactly the same thing, but this image might have been captured in a slightly different orientation. Even that cannot be accounted for when you are using template matching. Even you might have taken in the same orientation, but there could be some background changes. See here, the kind of wall or other background items you have are different from what you have here. And in the correlation, although you just fit your template close to that, anyway, because it has to account for this and this length, this part also would come there. And once this part comes, if in that region what you have, the content in the background is different, that also would cause you a problem on this. So in many, in a very constrained situation, this would give you ideal results. Otherwise this template matching could fail, right? And even intuitively, if you look at, we don't do to identify objects, as a human you don't process things by looking into, you put it there, do the do the subtraction of the corresponding intensity square. That's not how we identify objects. Say for example, tell me what is this object?
Lion.
Lion, right? A car here, elephant here, a flight here. But see, we are not at all looking into the content here. All that you had is a line drawings here, nothing more here. Even from the line drawings we are interpreting things. That means this is an interesting observation. Of course most of you, all of us know it implicitly, except that we are making an explicit statement here. Look, this is not the way we are doing. So how are we identifying things here? Based on what features are we identifying it? The feature is not patchwise mean square error or patchwise correlation. We are not really, you are not at all given any information about what is there here in this region. Okay, a very abstract drawing has been given to all of us, but everybody, okay, is able to figure out what that object is. So then, to recognize an object, to identify an object, what is the feature that we are using?
Edges.
That's right, edges. Edges play a very vital role in detecting the objects. So that's why we would spend this class, next class, and also after that a few more classes as well on identifying the edges. How do you identify edges? What exactly edges would convey? What kind of information are they going to convey? These are the things that we are going to take a look at. So again, we are going to see or introspect in more detail on what all contribute to edges. Okay, so suppose I'll just will not show you that image. I'll show you that a little later, but just think within yourself, okay, and try to visualize the objects we are looking, and try to answer me on what all information in a given image would contribute to edges. So you're seeing a digital image, okay, you don't require any edge detectors to apply. We all do it by default. We are trying to do that, we do it. But what is the kind of information or nature of information that results in edges in a given image? You answer me that.
Sharp changes in intensity.
Very good. Sharp changes in intensities would contribute to edges. Is there any other? That's one kind of edge that you would get. Any other kind of edge can you identify?
The slopes of all in all directions,
The slope in?
particular direction actually.
Yeah. So I get your point. So I'm just seeing there is a discontinuity in surfaces, in other words, right? So one object orientation is in a particular way and there is a discontinuity in that surface profile. That's what you mean, right?
Hmm.
Yes, that's correct. Any other point?
Changes in color.
Changes in color. Very good. If you are looking into a color image, of course, we all see the color. So you are right. If there is any change in color, we attribute that gets attributed to kind of edges there, right? That's what you mean, isn't it?
Yeah. Yes, sir.
Yeah, agreed. Just that now we want to restrict ourselves to grayscale images. Otherwise, you have a very valid, that's a very valid, valid reason to get an edge. One of the reasons to get an edge.
Yes, sir.
Very good. So that's like what the point that to add to the first one of you students has mentioned. He has mentioned like there is a step discontinuity in your edge profile. There is one color here. There is a sudden jump to another color. If you are looking in terms of intensities, if you are plotting, there is another thing. Now what has been told is it need not be a step edge, but could be a ramp edge also. That also is one type of edge. Any other thing?
Sir, change in a pattern maybe. So if we have a texture behind and we
Very
have an
good.
object before.
Very good. Very good. Texture also contributes to edges. Any other point? I'm sure.
Boundaries of an object.
Right. So boundaries of an object, instead of saying that, I want you to rephrase it a bit in terms of depth of an depth of objects or whatever it is there in within the given image. In terms of depth, I want you to restate your statement.
Is it that shadow?
That's right. Shadow also could contribute to NH, right? And look at here, you see the surface of it is in this manner here, right? After that, it has changed here. The surface had a discontinuity in this manner, okay? So that is change of the surface profile is there. And in terms of object and even background, one of you are almost stating it, except that I am slightly refining and rephrasing it. When there is a depth change of depth, look that you kept this pen here, okay? I am standing here, okay? You are still seeing an image there, okay? Video, but each one is a frame. You could see an edge here. Of course, we are all seeing color, and because of that also you are seeing it. Even otherwise, even if in case of a grayscale difference also, as there is a depth variation, okay, that would bring a change in the illumination. And also these two are different objects in a way, right? Except that now everything got smashed to a 2D yeah, a 2D surface. You are seeing the moment you're on a 2D plane, you are looking at, but change of depth is also something that would contribute to edges. So to put it more crisply, here we are stating kind of four. There are few other things also. One of you had rightly pointed out the texture. We will see it shortly. Surface normal discontinuity would contribute to edges here. Till here, if you look at the cap, I wish I have it something, but again, this is also fine. When you are looking at it, there is this is your surface normal is in this direction. Now this surface has come. This has a normal in this direction. So surface normal discontinuity would contribute to edges. Depth discontinuity. Okay. So if you look at this way, this object, this depth, this is all at the same depth. By depth, you are all, I guess, are able to feel what I mean. If you are looking from there and figuring out how far it is from the camera, this is at all at the same distance. Okay. And again, of course, you consider it in this manner. Okay. This is at one distance. Now this other end has come at a different distance. So that depth discontinuity would contribute to edges. Surface color discontinuities would contribute to edges, and shadow is nothing but illumination discontinuity. That also would contribute to edges. So that let's move on from a cartoon like picture to a more realistic picture that would more or less have all these kinds of phenomena happening and all these phenomena contributing to edges. Okay. Now don't pay attention to reading those texts, but just try to infer yourself. You see an edge here, right? And similarly, you see an edge here. Why are we seeing that edge? See, the background intensity is almost the same, except that few changes are there. But still you see the edge here because there is, after that you have the sky there. Okay, there is a discontinuity, depth discontinuity is coming. Here also you have a pillar. Before that there is a kind of platform here, and then there is this construction of this tower is there, not pillar, tower. So that is giving you one discontinuity here. Okay, and then one of you rightly pointed out texture. What does texture do? What texture does is it brings a change in the reflectance or appearance, and that's why you have here, you could see some edges here. Then shadows are variations in the intensity. See here, this structure is actually there projected forwards, but because the way the sun is somewhere around here projecting on that, and because of that you could see a shadow here, that's again contributing to edges. And then there is a orientation change, that's what we refer to as normal, surface normal. So here, till here, this is projected in this manner because the moment the surface normal changes, when light is falling on it, how it gets reflected, that is going to change there. So these all would contribute to having edges in the image. And this picture tells us that with even the minimal information of edges, we are able to very comfortably, okay, effortlessly, we are able to recognize it without any problem at all. And even for us, in some cases, that's a unnecessary information in a way. Even if you give it, if the goal is to just figure out what the object is, this is more than enough for us, isn't it? So now notice here how we are moving. So first we started with just image to image getting, then we started inferring what is there, where we are using the entire information. Now we notice that, well, we don't really need all the information. Sometimes that information could be misleading as well. What carries most information is edges, or at least edges carry definitely. There could be other features also that carry more information to detect edges. We'll see more and more as we move on, but edges for sure have very important information. We also have seen now what all could contribute to edges. Now the next obvious question would be, how do you get edges? Again, to simplify things, let's start with a 1D case. Okay, let's gradually move to a 2D image, but I give you a 1D signal. Okay, well, what do you mean by 1D signal? Assume that I am just extracting one row here from this image. I want to figure out at which pixels there are edges. How do you compute it?
Sir, if
Hmm.
the signal is maybe x of I,
Hmm.
then x of I plus 1 minus x of I whole square,
Hmm.
if we compute that for all I,
Right.
then above a certain threshold we can classify it as an edge. And
Very good. Very good. You are right. So what you are saying here is, since there is a sudden change here, why not look at the difference between the current pixel and either the previous pixel or the next pixel? Take the difference. Okay. Just to edge can be from dark to bright or bright to dark. So in order to account for that, you are taking square of it, and then you are putting a threshold on it, because here also there is some change if you are moving, but at an edge you are expecting a high change there, correct? So that's why you are putting a threshold on it. So everything is there, all the three aspects are there in the in the function that you have mentioned. You mentioned x of I plus 1 minus x of I whole square, right? So that means the transformation now can be, the movement now can be from either to dark, from either from bright to dark, or from dark to bright, right? That square is taking that difference, is making sure that there is a jump there. and then you apply a threshold that's telling you that you will put a upper cap, and anything above that, if it is moving, then you consider it as NH. Very good. Let's move to continuous case for some time. Okay, suppose I give you, let's talk in terms of math now. I give you a function f of x. Okay, x could be, you could think it is varying. Now you tell me it's a you told it for in discrete case I plus 1 minus I. Now for an f of x, now how would you say whether there is an edge, where there is an edge? So in other words, you want to find out a jump there. So what is the operation that you do on f of x to find it out?
Differentiation.
Very good. So you just need to find out the derivative of that function with respect to x itself, right? So you are finding out pixel location, next location, and this location is what you are looking at. That f of x is having intensities, but what you are going to find out is df by dx, and then you again put a threshold there that would give you an edge. Instead of giving you f of x, now I give you f of x comma y, okay, which is nothing but, assume this continuous for a moment, okay, or a discretized version of that. Now if I give you f, so if I had given you f of x, you compute df by dx, and you would see wherever there is a sudden change, what would happen to df by dx? It would have, for a small value of change in your f value with respect to x, there is a large value change in that function value f. That's what your derivative is telling you. Now I have given you a function of x comma y. It's not anymore a function of x. It could vary both along the row and along the columns as well. That's what you have a 2D image. Now how do you find out an edge?
We'll take
No, to do
derivative
the same
with
thing,
respect to both,
x
with
and
respect
y.
to x and y.
Then what will you do? There you are right.
So
Then what will you do?
vector sum of both the gradients.
Vector sum. So how do you give some term now with respect to derivative with respect to x for f of xy? How are you going to refer it to? What is the
Dou
function?
f
Right, dou f
dou
by,
f by dou x.
very good, dou f by dou x. With respect to y is
Dou f by dou y.
very good. Now I give you a location x comma y. How would you say whether there is an edge or not at that point? You have now two values now, right? Dou f by dou x is there and dou f by dou y is there. How would you say whether there is a strong edge or not at that point? Yeah,
How you find out magnitude and the direction?
yeah. What is the magnitude there?
Is
You
a
are
square
right.
root of
Square root of,
both magnitude.
that's
Square
it.
of both magnitude.
That's it.
And tan inverse of y by x.
What is it going to give you?
Direction.
Direction. Very good. So the moment you are coming from 1D to 2D, your derivative in 1D, you refer it in 2D to something else. When you have both dou f by dou x and dou f by dou y, what is it referred to as? I'm sure some of you have heard this. It's a derivative there. Now I have a parameter. Now I have what I have now is dou f by dou x and dou f by dou y. This is referred to as, you refer to it as gradient, and the magnitude of gradient, as one of you had rightly pointed out, would be sum of squares of the derivatives, partial derivatives to be more precise, in x and y, and the direction of that you would get it by taking tan inverse of y by x, that dou f by dou y by dou f by dou x. That's what you would be getting there. Clear so far? So we covered it quite fast, since you are able to take me through without any problem there. Okay, so maybe just few illustrations. This is nothing new now. You all of you have together answered all those things, but just let's have a quick look at it. It just look like steep cliffs. So this is where intensity is plotted as a surface here. Wherever there is an edge here, if you look at the surface plot, that's where this is a plot being of intensities, there is a sudden jump. or a big jump there. If not sudden jump, there is a big jump there. In terms of intensities, for example, even if you look at it in 2D, this is how, for example, 33, 25, 26, all of them is having one value. This is another value. So this is something where you have a jump here. So this kind of, this edge is something like this here when you see it microscopically. And now let's take a very simple case here where you just, anyway, all rows are same here. Purposefully to simplify things, it has been done. So you take profile of these intensities across any of these rows. So it would look like this. There is one value here and this is all black. So let's say this is 255. This has come to 0. Okay. And the moment you came here, again, this has become 255. We want to avoid plotting surface plot. So what we did is a 2D where all rows are same, and for one row we are plotting now intensity, which we could do it in 2D. That's the whole trick we are doing it. Now for this, if you are taking a derivative here, you are moving from you are taking f of x plus 1 minus f of x. If you are taking, okay, that's as a derivative. Well, that value, the value before it is smaller, so that's why you would get now this again a an extrema here, minimum here, and then moving from dark to bright, you get an extrema maximum there. So now that tells us that derivative does have information about edges, particularly when you are looking at a 1D profile. Now we are from there, this differential, if you have to deal with things in 2D, that's where this is referred to as now differential operators, where the gradient is referred to as, so be very clear, there are derivative, there is gradient. Okay. Slightly thing that we could miss, although very similar but not exactly same, is edge need not necessarily be the gradient. All that we are saying is at an edge there is usually a gradient. Okay, just make a note of this point. Don't worry at this point. I'll talk about it later when we are doing other edge detection methods. All that we are saying right now is at an edge we could have a gradient. That's all we are making a comment right now, or a derivative change. Okay, so when it comes to 2D, we write it as, you already pointed it out, this is we refer to as gradient. Now what if you have a horizontal edge? How would be the gradient? What if you have a vertical edge? How would then the gradient? What if the edge is oriented in some other direction? That is all. We have an example here. Notice here, if I am moving vertically here in this image, there is no intensity difference. So you could see here dou f by dou y is 0, right? Consider this vertically, there is y. Okay, again we keep changing this based on our convenience, but here you consider this is your y direction. If you are moving in y direction, there is no change in intensity, so that's dou f by dou y is 0. Something like this, if you have it, then as you move in this direction there is a change. Dou f by dou x is non-zero there. That's all, you have the value there. And another very very important point you should keep it in mind is the edge is not in the direction of gradient. Okay, keep this in mind. What is the relationship between the edge and the gradient? Edge and gradient are not same. What's the relationship between the edge and gradient, at least in these examples?
They're perpendicular to each other.
That's right. Edge. So edge is, gradient is perpendicular to the edge. Okay. Suppose you have a horizontal edge here. This is your y direction. Assume that. So if you are moving in this direction, there is a change. So you have a non-zero dou f by dou y. Whereas if you are moving in this direction, that's dou f by dou x is 0. This is the edge. Okay, now this being y direction here, this second component you have. So be very clear. If I ask you to find out a horizontal gradient, if you have a or in other words, if you have a non-zero gradient in the horizontal direction, that means you have a vertical edge. And if you have a z, and the other way around. Okay, hope this point is clear to everyone. Any question here? right? And there is no hard and fast rule that we should have only horizontal and vertical edges, right? Edge could be in any other directions. Okay, otherwise we all would be having only rectangular objects. That's not the case. So here, if you look at it, the variation could be in this direction. As you are moving in this direction, if it is changing, so you notice here the intensities are changing as you move from this corner to the other corner diagonally in the diagonal orientation. That means you have dou f by dou x, dou f by dou y. But again, be clear that this direction is still perpendicular to the edge, but that relation would remain same. But once you know the angle of the gradient, you can always tell what is the angle of your edge. Okay, that is given by now dou f by dou y divided by dou f by dou x tan inverse. Okay, what is the range within which you could get this theta values now, orientation angles? I'll here just remind you of what you have done in case of phase unwrapping, okay, that you have come across in DSP. Now you tell me.
The principal value is 0 to pi.
Correct.
Anything
So
over that is a repeat.
that is true. But tan inverse as such would give you from 0 to pi by 2 only. So how do you extend it from 0 to pi? That's the question.
We take the explicit directions of into consideration.
Right. Explicit signs of your dou f by dou y and dou f by dou x are, in other words, the explicit sign of the numerator and denominator. If you are keeping track of them, you will get from 0 to pi, right? This has been discussed in your DSP course. Oh, right. Hope you remember that. Otherwise, you just refer back on how. Yeah. So just a quick question here. What is the function in that case you would use in MATLAB? Since you guys have done MATLAB, DSP, you have done maybe lab, I think you had it. So quickly tell me, to find out this data, if you had to find out given these two values, what is the function you would use in MATLAB? Yeah, normally you will use a tan, but here if you want to keep track of numerator and denominator separately, you use a function a tan2 is there. A tan, after that number 2 will be there, which will take as an arguments separately numerator and denominator, so that you could pass to it the values of along with signs. You could pass the magnitudes of numerator and denominator explicitly and separately. Okay, there should be some such function, equivalent function in Python. Figure it out for yourself there. Okay, so that's it. So what we would do, we will stop here for this class, and in the next class what we are going to do is how are we going to compute these gradients using spatial filtering. That's what we will do in the next class on Monday.